Welcome to a lesson with Dr. Powell. Let's take a look at computing the slope of the tangent line of a function at a particular point using a limit and synthetic division, assuming that the function is a polynomial function. All right, so this is kind of a straightforward way to carry out the limit computation for any polynomial function if we want to find the slope of the tangent line at a specific point, in this case at x equals 1. Okay, so to do that, we're going to first write down 2 points that we want to focus on finding the slope of the line segment in between. One of them is simply going to be at 1, x equals 1, and you plug 1 into the function, and you're going to get 3 minus 1 plus 1, that's just 3, so 1, 3 is one of the points. The other point on the curve, right here, we're just going to pick a point that's arbitrarily close to 1, so the x value, we'll just call the x value a, and we're going to consider what happens as that x value moves in and narrows to 1, closes in on 1. All right, now what's the y value at a? Well, you just plug in a, and then into the function, and then we'll just have 3a to the 4th minus a squared plus a. All right, so then rise over run, like the slope of the line segment between these 2 points. We want to look at that slope and then imagine what happens to it as a gets close and close to 1. All right, so as we do that, let's see, we have just this y value minus that y value. We'll just subtract the y values down this way. It'll work if you go the other way. However, computationally, it's easier. It's just more straightforward just this way. So we're just going to subtract down on the y's, and we end up getting 3a to the 4th minus a squared plus a minus 3. Subtract down on the x's, so that's rise over run, change of y over change of x, a minus 1. And the goal is to find what's called the limit of this expression as a approaches 1. And we're going to do that. Well, what does that mean? That means this expression, which represents the slope of the line segment between these 2 points, as a narrows in on 1, we look at the slope, and what is the output of this expression getting close to? Notice that we can't plug in a equals 1 because to the expression, because it's not defined. We can't divide by 0. But however, as a gets closer to 1, kind of think on a curve. You know, if you have a curve and you have 2 points and one of the points is narrowing in on the other one, the slope of the line segment between those guys, as this guy gets closer and closer, will approach what you call the slope of the tangent line, which is the slope of the curve that the curve most looks like if you narrow in on that point. So we should be getting that. Now, this expression right here, we can't plug 1 into it, but we're going to algebraically compute exactly what that tangent line slope is. We're not going to simply just plug in values of a close to 1. We're actually going to do this. We think about this expression and consider an algebraically equivalent version of it that we can plug 1 into. Remember that if you algebraically rewrite something in an equivalent form, you can actually change the domain. Just like if you cancel a factor on the bottom to the top, algebraically they're equivalent, but we've removed the domain restriction. So similarly, we can do something here using a fundamental idea. As these 2 points are narrowing in, think about the rise and the run. Isn't the rise going to 0? And the run is also going to 0. Both of them are going to 0. Now for polynomials, if a minus 1 is 0, and this guy up here is equal to 0 for the same, so meaning, at the same time when a is going to be equaling 1. So when a is equal to 1, that makes this guy 0, a equals 1 makes that guy 0, a minus 1 is actually going to be a factor at the top. That works that way for polynomials, which means a minus 1 evenly divides the top. This works every time for a polynomial function, meaning that we can actually just do division. We can just divide the bottom into the top and get an expression where the domain is changed and just plug in 1 and be done. It's a very simple way of combating such a limit. So we're going to do some synthetic division and put our coefficients as they should be. 3a to the 4th, 0 a cubed, use a placeholder, negative 1 a squared, 1 times a, negative 3. Notice that a is our variable. That's what's changing and moving. Okay, we're dividing by a minus 1. We change the sign of that negative 1 to a positive 1 here. And we're going to have a remainder coming out in one place right there. We proceed with synthetic division. Drop the 3. 3, add. And then we get 2, multiply, 2. We get 3, 0 as expected. It did evenly divide, and we get, and this is going to be equal to an expression. I'll keep what we're trying to do right here. We're taking the limit of this expression, so this expression algebraically is equal to something even though the domain has changed. It's 3a cubed, and I'm reading it right off of this. This is 0th power, 1st, 2nd, 3rd, so 3a cubed plus 3a squared plus 2a plus 3. Now simply we can just plug in the 1 into all of this, and we end up getting 3 plus 3 plus 2 plus 3, which ends up being 11. Okay, that tells us that the slope of this function at the point x equals 1 is simply 11. Thanks for watching.